Hello everyone. Have you ever tasted a lemon and felt that sharp soreness, or touched soap and noticed its slippery feel? These everyday sensations are our first encounters with acids and bases. Acids, like vinegar and tamarind, are sour and turn blue litmus paper red, while bases, like soap or washing soda, feel soapy and turn red litmus blue. When acids and bases meet, they react to form salts and water, like hydrochloric acid reacting with sodium hydroxide to give sodium chloride and water. So, acids, bases, and salts are not just textbook concepts, they're a part of your kitchen, your bathroom, and even your own stomach.
Now let's go back to one of the earliest definitions. According to Arrhenius, acids are substances that release hydrogen ions, written as H plus in water. For example, hydrochloric acid dissociates as HCl gives H plus plus Cl minus. Bases, on the other hand, release hydroxyl ions, written as O minus in water. For instance, sodium hydroxide gives Na plus and O minus ions. This simple view explains why acids and bases react in water, but it only works in aqueous solutions. So, while useful, the Arrhenius concept is a bit limited in scope. Chemistry grew beyond this with Brensted and Lowry in 1923. They defined acids as proton donors and bases as proton acceptors. This idea is broader because it works even when water isn't the solvent. Let's take the case of ammonia in water. Ammonia accepts a proton from water, forming ammonium ion NH+ and hydroxide OH-. Here, ammonia acts as a base and water as an acid. This theory also introduced the very important idea of conjugate acid-base pairs. Every acid has a conjugate base, and every base has a conjugate acid. They differ only by one proton. Let's make this clearer with an example. When hydrochloric acid reacts with water, HCl donates a proton to HO. So HCl is the acid, and its conjugate base is chloride ion, Cl-. Water acts as the base, and its conjugate acid is the hydronium ion, HO+. Notice the pattern. Strong acids have weak conjugate bases, and strong bases have weak conjugate acids. Every acid-base equilibrium always involves two conjugate pairs. This is a very important tool for predicting the direction of chemical reactions. Another giant step came with Jean Lewis in 1923, who defined acids and bases without even mentioning protons. According to Lewis, an acid is an electron pair acceptor, while a base is an electron pair donor. For example, boron trifluoride, BF, has an empty orbital and accepts a lone pair of electrons from ammonia, NH. This forms a stable BF point NH adduct. The Lewis concept explains reactions in coordination chemistry, catalysis, and even organic synthesis. So now acids and bases are no longer just about hydrogen ions, they are about the flow of electron pairs. Let's practice this with some examples. What are the conjugate bases for HF, HSO, and HCO-? They are F-, HSO-, and co-superscript 2 respectively, each obtained by removing a proton. Similarly, what are the conjugate acids of NH-, NH, and HCOO-? They are NH, NH+, and HCOOH, obtained by adding a proton. Here's a quick rule to remember. The conjugate acid always has one extra proton compared to the base, and the conjugate base has one less proton compared to the acid. These pairs are essential for mastering acid-base equilibrium problems. Now, where do we use these ideas? Arrhenius theory explains simple neutralization reactions like vinegar reacting with baking soda. Brensted-Lowry theory explains buffer solutions that maintain pH in our blood or in lab experiments. And the Lewis theory? That's the backbone of catalysis and many industrial processes. Think of hydrochloric acid in your stomach helping digestion, ammonium salts and fertilizers boosting crops, and alkalis like sodium hydroxide in soap making. Acids, bases, and salts connect theory to life in the most direct way. So, to wrap up, acids, bases, and salts may seem like basic definitions, but they are powerful ideas that explain chemical reactions everywhere in your body, in industries, and in laboratories. Arrhenius gave us the hydrogen and hydroxyl view, Brensted Lowry introduced conjugate pairs, and Lewis expanded it all to electron pairs. Together, these concepts form the foundation of acid-base chemistry. I hope you now see how fascinating and alive these definitions are. In our next session, we'll explore even more exciting aspects of equilibrium. Until then, keep noticing chemistry in the world around you.